Well, welcome. So make this little video in substitution for class today. Since it's still Tuesday, I'll tell you the verse for the day, which was Genesis 1:1. In the beginning, God created the heavens and the earth. This verse was given to me by my son Benjamin, and I think it's a good verse. Let's see here. Now, so today I need to look with you guys at systems of linear equations and the Gauss-Jordan elimination method. Now, so let me just get straight into it. There's some language we need, which is, what is a system of equations? So I kind of talked about it, but I didn't give you the full definition last class. And here's the full definition. So if we have n x1 through xn variables, and then aij, bi, real numbers. So I is the row index, it ranges from 1 to m. And here j is the column index, and it ranges from 1 to n. Here, so basically we're looking at m as in mummy, equations in n variables, n as in nanu. And anyway, this is a system of linear equations with coefficients aij. And this is, I think this usually I would call this like standard, maybe standard scalar form or something, but we'll later talk about standard matrix form, in which case you're talking about a matrix specifically, but we'll get there. For today anyway, though, let's just talk about a system of linear equations with coefficients aij. And the b1 through bm, these are the so-called inhomogeneous terms. The reason they're called inhomogeneous terms is if even one of them is non-zero, then that makes this system altogether inhomogeneous. On the other hand, if all of the inhomogeneous terms are identically vanishing, if they're all zero, then the system is said to be homogeneous. Fun fact, a homogeneous solution always has at least one solution. It always has the zero solution, because if the system is homogeneous, you can just put all the variables equal to zero and it works. And so that makes zero a solution to the system. And by zero, I mean the vector 0, 0, 0, 0, so forth and so on. Now, generally speaking, the solution set is the collection of all x, which is an n-tuple, x1 through xn in Rn, which simultaneously solve m equations of the system all at once. Now, we looked last time at some strategies and techniques for understanding what this means geometrically in the case of, two equations and two unknowns, or I guess three equations and two unknowns. And I talked a little bit about what it means geometrically for three unknowns. Now, past three unknowns, the geometry gets a little sketchy in terms of direct visualization, but our methods, our algebraic methods, can work just as well with three variables as they can with 33 or 3,000, as you might do in an industrial setting. Now, so since it doesn't give us joy to write all the variables out every time, we're going to learn that we can replace, the star system, which I had up here, with instead just the numbers, the coefficients that form the system. So that's the so-called augmented coefficient matrix. This is a m by n plus 1. So we talk about an m by n matrix. That means it's got m rows and n columns. Our focus will be just on matrix structure and nomenclature in like the next chapter, so I'm not going to belabor it here. But anyway, we are at least using matrices for bookkeeping right now. They take on a life of their own in about a week. Okay, so this augmented coefficient matrix just has the numbers that are the coefficients from the system, and the last term, the last column, if you will, is the inhomogeneous column, or it's the home of all the inhomogeneous terms. If any one of these is non-zero, then it corresponds to an inhomogeneous system. By the way, the first n columns we just call the coefficient matrix. The coefficient matrix, it's got nothing to do with the inhomogeneous terms directly, and it's just that is what it is. Now, so I started to tell you guys last time that there are different things we could do to a system of equations, and in so doing, not change the solution set, right? They'd be the same system. And so let me just recap that. There's three elementary row operations, although truth be told, guys, I don't always insist that we only use elementary row operations, but my notes define these as the elementary row operations, and so that's what they are. However, there are composite row operations that we often do, as you'll see in my examples. All right. So like what I mean by composite is, for example, row subtraction. You could think of as multiplication of the one row by -1, and then adding that -1 multiplied row to the other, right? That'd be like row subtraction is multiplication, is addition of the additive negation. Well, that's the only kind of negation there is. Anyway, so you got your non-scalar, non-zero row rescaling, you got your row addition, and your row swap. These are your elementary row operations, all right? And let's just look at an example. I have a number of examples that will help just reinforce this method, and I'm going to use these examples as a means of introducing terminology. I mean, yeah, sure, I could try to define the terms in the abstract, but you know, I think it's probably easier for you to follow if I just put numbers in and just do some examples and explain the terms in the examples, as opposed to trying to come up with some generally abstract definition, which would just confuse you. We'll save that for 321. Okay, anyway, sorry, I'll stop. Most of you are like, haha, I don't have to take 321. Anyway, let's see here. No, wait a minute. No, being a math major is a reward, not a punishment. You should all be math majors. What am I talking about? So here's a system. We've got four equations. It's going to be 2 equations and 4 unknowns. X1 plus x2 plus x3 plus 2x4 equal to 10, and 2x1 plus 4x2 plus 6x3 minus 10x4 equal to 0. So this is an inhomogeneous system because of the 10, all right? Now I can trade that for its augmented coefficient matrix right about here. And as you can see, I just rip off the numbers and keep the inhomogeneous terms here. So my opening move was to so this one I'm really trying to stick with just elementary row operations. I want to show you that we can use just elementary row operations to put the matrix in a certain form, which we're going to call the reduced row echelon form. All right, now, so here, let's get started. So I divide or multiply the second row by -1/2. In so doing, this becomes -1, -2, -3, and 5, and 0 divided by -2 is still 0. Oh, by the way, I haven't checked these. So usually when I give this lecture, I make all kinds of arithmetic mistakes, which you guys correct because we have this thing called a classroom where we have this classroom experience. But since I'm just making this video, the odds of me making a mistake and just reinforcing it are pretty high. So if I do make a mistake and you notice it, by all means, email me. So maybe I'll find it. Let's be optimistic. I did not make a mistake in the making of these notes. Let's go here. So divided by -2, so we get to that. And then my next move is to add row 2 to row 1. So the notation I use is the first thing that's noted, the first thing that's denoted is the one that's modified. All right, if I was to write row 1 plus row 2 rather, the 1 and the 2 flipped, then that would mean I was adding the previous row 2 to the previous row 1 to replace the new row 1. But here I kept row 1 the same, and row 2 is the one that was modified. See, 1 plus -1, 0, 1 plus -2 is -1, 1 plus -3 is -2, 2 plus 5 is 7, 10 plus 0 is 10. Okay, whew. Well, hopefully no arithmetic mistakes just yet. All right, now next move, down here, continuing, I do row 1 plus row 2. Now I'm modifying the existing row 1 by adding the previous row 2. So 0 plus 1 is 1, -1 plus 1 is 0, -2 plus 1 is -1, 7 plus 2 is 9, 10 plus 10 is 20. There you have it. Next thing I do was I multiplied row 2 by -1. And so that gives me 1, 0, -1, 9, 20. Nothing happened to the first row, and the second row becomes 0, 1, 2, -7, -10. And this is what's called the reduced row echelon form of A. All right? Now, and what does this mean? Well, this means that the given system of equations, right, star, is equivalent to the one I've written in brown here. And so, like, this is just x1 minus x3 plus 9x4 equal to 20, and x2, plus 2x3 minus 7x4 equals to minus 10, which I can solve for x1 and x2, right? And it gives me this and that. And so my solution set, I put the formula for x1 here, I put the formula for x2 there, x3 and x4 are what are called parameters here. They're free parameters of the solution. In other words, this solution is what you'd call a two-dimensional solution. It's got two free parameters. So geometrically, the solution set's like a plane in 4 dimensions. Anyway, so here, the first 2 columns are what we call E1 and E2. So one of the things I'm going to be pointing out is when we do the row reduction properly, the end result is that the pivot columns, the leading, any row, any non-zero row, the leftmost entry in that row will be 1, and it'll be the only one in that column, which is, there's not much to see here in terms of like the meaning of pivot column, but pivot columns are going to be just ones with all zeros, except for the one, there's just one and the rest are zeros, okay? But to recap here, E1 and E2 are the column 1 and column 2 in the row RREF here, and you notice that the third and the fourth columns correspond to the parameters in the solution set. This will always be the case. When we do the row reduction, the non-pivot columns, the variables corresponding to the non-pivot columns will appear as parameters in the solution set, as supposing, of course, that the system is consistent. All right. Well, let's go on here. So I'm going to do one more example, and then I will tell you the quote-unquote algorithm. All right. But before I do that, let me just a couple more examples, then I'll tell you the algorithm that I'm kind of sort of using. Truth of the matter is I don't quite follow the algorithm. I follow what's sort of most convenient. But I'm trying to stick closer to the algorithm, at least to start with here, just so you can kind of see it. All right, so there's 2 aspects to the algorithm. There's what's called the forward pass and the backwards pass. So the forward pass, well, let's just look at it. So here's my system of 3 equations and 3 unknowns. That gives me a 3x4 augmented coefficient matrix, 3 columns, 3 rows, 4 columns rather. And so I get to work here by basically my first pivot position, as it's called, is this upper one. All right, and what my goal is to eliminate anything below that to make it 0. And so I achieve that goal by saying row 3 minus row 1. Row 3 minus row 1 clears this 1 out as such. So and already this is not technically an elementary row operation, but we allow it, okay? Let's see here. So row 3 minus row 1 is, well, 0. And minus 2 minus 1 is minus 3. 1 minus 1, 0. So we get 0 minus 3, 0. And of course, 0 minus 6 is also known as minus 6. There we go. At this point, we have cleared out everything. So like, let me just make a little comment here. By the way, I will scan these and post them once I get a chance, hopefully tomorrow. If I can make it to school on the roads being so dangerous. Let's see here. So this column here is, pivot column. We've got, all entries below pivot position, all zeroed out. Woohoo! That means we're done with that one. All right. Now some books, what they'll do is they have this system of like shading things that they're done with to move on, something like that. I don't want to shade, and I think I have a PDF handout my brother makes for linear algebra posted on my website. He's got that shading thing in there if you want to see it. But anyway, nobody's going to shade their work, so it's just kind of a new, just to help you learn. Anyway, so my point is we're kind of ignoring that for the moment once we get past that. So we move on to the next column. And in this one, you could either pick this one or that one as your pivot position. If I've got a 1 in one of the spots, I'll use the 1 because it's just easier to do arithmetic with the 1. So I've picked that as my pivot position. Then my next goal is to eliminate anything below the 1, namely this -3. I achieve that by adding 3 times row 2 to row 3. So I replace my old row 3 with old row 3 plus 3 times row 2. Now rows 1 and row 2 are unmodified. We're just changing row 3. So let's see here. Row 3 plus 3 times row 2. So 1 plus 3 times 0 is 1. Wait a minute. My bad. 0 plus 3 times 0 is still 0. -3 plus 3 times 1 is 3 minus 3 plus 3, which is 0. 0 plus 3 times 1 is 3. -6 plus 3 times 5 is -6 plus 15, which is 9. Okay, good. Phew. Now, at this point, I have finished this right here. Technically speaking, guys, is what you might call the REF of the matrix we're reducing. Okay? Now, REF is just reduced echelon form. Echelon's just a fancy word for stair step. So it looks like a stair step, but it's not. First of all, it turns out in general, when you're doing these kind of steps, you can get to different things above the pivot positions. Like this is not unique, so I'm reluctant to say that this is the REF. It's really an REF. There could be others. So I put some quotes around that because, like, okay, fine, for a given calculator, if you have like a Texas Instruments calculator, they'll calculate REF. I don't know why you'd want to. Honestly, like I want the RREF, the reduced row echelon form, because that, in contrast to the REF, is unique. All right. So here's how that goes. Now, what I made in black here. So, all right. So what I've done in purple in my notes, I describe as quote unquote the forward pass. So the forward pass involves identifying pivot positions, possibly swapping rows to make things go into the upper row if you don't have one to start with. So basically, you want your first pivot to be like a 1 as high up as you can get in the leftmost column that you can achieve. If you have your like leftmost column as zeros, then you can't put a pivot position in the leftmost column. All right. I don't think any of my examples have that, but it could happen. All right. So if the leftmost column in your matrix is non-zero, that means that you can make the upper, like the highest corner spot in the matrix, you can make it a pivot. And after you're done with the row operations, you should have E1. You should have 1, 0, 0 in that first pivot column. And then as you go across, going to the next pivot and to the next, you're gonna clear out non-zero entries below your pivot position. All right. And at the end of that, you're not going to have E1 and E2 and E3 in this case. Like these are not E2 and E3 because this would be like 1, 1, 0, of course, and 1, 1, 1. But this is the forward pass. So the forward pass gets you to a pretty nice system. If you were to write this down, this is the system that we could solve with back substitution like we did in the first class, right? It's actually pretty easy to solve the system from this, but we don't want pretty easy, we want stupidly easy. So stupidly easy happens after we do the backwards pass. The backwards pass, so forward pass kind of goes from the leftmost column to the rightmost column, all right? Well, to the rightmost pivot column, all right? We go kind of left to right, forward pass. And then the backwards pass goes the other way, starting with the last thing, which was in this case the third one. So that we take the third one, and let's see here, I do row 1. Oh man, son of a gun. Well, I didn't do it quite in the right order. Like I said, I don't always follow the algorithm. Like technically the backwards pass, it should be done like the last pivot column, you sweep up that one, and then you go to the next to last and sweep up that one. And you systematically go across, clearing out everything that's non-zero above the pivots. I just decided to do row 1 minus row 2 because it jumped out at me. So I'm replacing old row 1 with old row 1 minus row 2, which basically just takes these two ones and cancels out those two ones, right? Which just leaves you 1, 0, 0, 1 and then 0, 1, 1, 5. And then I did row 2 minus row 3, which is going to take old row 2 here minus old row 3 here. That cancels this one out. And then 5 minus 3 is 2. Okay, so then we get to this lovely... Now this right here, once you've got every non-zero row has a leading... the leading entry, the leftmost entry in every non-zero row is a 1, all right? And above and below that 1 are just zeros. Once you've got that, that's the reduced row echelon form, and that's unique. No matter what sequence of row operations, elementary row operations you did, and even composite row operations, because those are, every composite row operation is just a composite of several elementary row operations. So whatever sequence of row operations you have so chosen to take, if once you get to the reduced row echelon form, it's unique. And not just that, it's beautiful, because once you get to the reduced row echelon form, there's no back substitution work left to do. You just read the solution off. This says z equals 3, y equals 2, x equals to 1. And so here, the solution is 1, 2, 3. The solution set is a singleton, a funny-looking set containing just one element. You know, a singleton. It sounds like an insult, right? You're such a singleton. All right. So again, here, just a little bit more, let me emphasize the language here. The first three columns are pivot columns. So here, E1 is 1, 0, 0, E2 is 0, 1, 0, E3 is 0, 0, 1. So you're like, wait, hold on, flag on the play. You said E1 was 1, 0, and E2 was 0, 1 in the previous example. That's right, I did. We use E1, E2, E3 in a context-dependent fashion. So depending on whether you're talking about three-dimensional vectors or two-dimensional vectors, you'll let your E1 and E2 be the appropriate size to match the context, all right? I'm not going to start writing like E13, so it's like the E1 basis in the three-dimensional context, right? Where would you need to do that? Well, you'd need to do that if you were programming something rather than just talking about it in math. All right, unless your computer language is pretty robust. Now here's another one. Here I have x1 plus x2 plus x3 plus 6x4 equal to 0, x2 plus x3 plus 5x4 equal to 0, x1 minus 2x2 plus x3 equal to 0. I call this the star-star system. Now the star-star system is homogeneous. And check it out, yo. So I take row 3 minus row 1, I get that. I take row 3 plus 3 row 2, I get that. I get row 3 over, divide by 3, I get that. I think I forgot to talk about that last time. What do I mean last time? Well, you notice if you compare examples 2 and examples 3, well, those are the same row operations. See that? So I did this, this, I did this, and what happened is, all that happened here is I've adjoined, since it's a homogeneous system, an extra column of zeros. Nothing happens when you do row operations. The zeros just add to zeros, and scalar multiply by 0, non-zero times 0 still 0, and nothing happens, right? That column of zeros just rides along. And it actually doesn't change anything if I make the 6, the 5, and the 0. In the original system, 6, 5, 0 were in homogeneous terms. In this example 3, 6, 5, and 0 were the coefficients of x4 in the coefficient matrix. Row reduction doesn't care whether that fourth column was the inhomogeneous term of example 2, or if it was the actual, part of the coefficient matrix in example 3. The row reduction steps are the same. That's why the row reduction steps are the same. And all that happens is the same steps as in example 2 happen in example 3. It's just the interpretation changes, you see. Now we've got 3 equations and 4 unknowns, which means I'm not going to have a unique solution. By the way, I should mention This is the case of a unique solution, right? A unique solution. A unique solution means there's just one solution. On the other hand, example 3 is far from unique. There is a parameter, and the parameter we use for the solution set here is x4, which corresponds to the non-pivot column. Notice that the first, the second, and the third columns are pivot columns. That's E1, E2, E3, like I was just talking about. And here's your solution set. We can always write the solution set for a consistent system as a set which is parameterized by the non-pivotal variables. Non-pivotal variables are variables which correspond to non-pivot columns. In your coefficient matrix, when you do the row reduction, every column will either be a pivot column or a non-pivot column. Correspondingly, in the solution set, the pivotal variables are dependent on the non-pivotal variables. This is how it works. This is how we write the so-called standard solution set. All right, so I think I said I would show you guys the algorithm. I guess I owe you that at this point. So here's my handy dandy notes, and let's see here. I know the printer's doing this funny fuzzifying stuff lately. Anyway, let me not distract. So I defined the M linear equations and M unknowns there, just like I did here for you guys. And then I talk about the augmented coefficient matrix. I have some examples in the notes which use a more, let me zoom in for a second here, at great risk of my power cord. I'm gonna have to get a new camera pretty soon. This power cord's getting really, really fussy lately. Anyway, so this notation, if you thirst for a more explicit notation, here it is. This says row 2 minus row 1 goes to row 2. Now, in my notation I've been showing up till today, I would have just wrote R2 minus row 1 goes to that, all right? But anyway, so got a couple more examples in here. Let me kind of let you read those. And then here I have, showed explicitly what the row operations look like for an arbitrary 3 by 3, 3 by 4, I suppose, matrix. Here's, scalar multiplication, row addition, row swap, right? In my 321 notes, I think I have, phooey. Oh no. Well, this is awkward. I have somehow managed to get a spasm in my leg. Yeah, it never happens when I'm lecturing. This evil chair was in my leg in just such a way. Oh man, that's bad. All right, I'll make it. I want to make it. So here's. I just have to relax and stand up. So this is the Gauss-Jordan algorithm. Steps, step 1, 2, 3, 4, 5, 6. Here it is. I'll let you read it. I mean, you can just mechanically follow these steps, and it will get you to the row reduction of any matrix. All right, and there's a proof that this is unique in Appendix E of Elementary Linear Algebra Matrix Approach by Spence, Insel, and Friedberg. I was trying to find that book to show you it for this talk, but I was not able to find it in my basement, which is currently being remodeled by me, which is a slow process since I'm teaching. All right, moving on here. So I'll let you read that, but it basically just says what I've said in words, which is try to make your pivot position as far to the left as you can. Swap rows if you need to make it go up to the top row in the matrix. Clear things out below that, and then go on to the next column. If possible, you go on to the next non-zero column. Swap rows if necessary to put a pivot column into the next highest possible row, and you just keep doing this. And that's the forward pass. And that once that's all done, you sweep out the positions above the pivot positions and make them 0, and that's the backwards pass. And eventually, you'll have every pivot column is a standard, is either, it's just a 1 with zeros in the rest. All right, sorry, I'm trying not to go into spasm again. Not cool. Anyway, it's a new one for me. So here is a yet another 3x4 matrix. How boring. But here I do a row operation, another row operation, and let's see, 1, 2, 3 row operations. That gets me to this. I said that's the REF, but depending on what calculator you use, sometimes like they insist on dividing by 5 and by 6 to have leading ones for the REF. It really depends on what book you're looking at in junk. But anyway, but according to Inzel, Spence, and Friedberg, this is the forward pass, all right? And then the backwards pass, what it does is it subtracts off the multiples of well, first of all, it rescales the third pivot column here by 1/6. And then once you have that, you use that to clear the zeros out above that 1. So I scooch up a bit here. So you use, let's see here. So we take that 6, divide by 6 to get that, and then use that 1 to clear these out to make them 0. So you bop, 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 bop. Then we get 1, 0, 0. So the third pivot column is now E3. And then you go on to the next one. He rescales that one by dividing by 1/5. That makes that into a 1. And then you use that 1 to clear the 2 out. This is the backwards pass. And then we're done. See, we've got E1, E2, E3, 1s. So every non-zero row has 1 in its leading leftmost position, and that 1 has zeros above and below it. All right? There is, of course, no above for the top one, and there is no below for the bottom one here, but you get the idea. So, yeah. Let's see here. This next one, I won't go over all the ones in the notes, but since I've got this here and I started talking about it, let me just finish. So this matrix, I start by clearing out I'm starting with pivot position 1 here. I'm clearing that 3 out by subtracting 3 times row 1 from row 2. And then I subtract 2 times row 1 from row 3. That gets me 1, 0, 0. Now this one's kind of cool because this time I cannot use the second column as a pivot column because it's because that 1 is behind the -1, like so. So I have to look in the so once I've finished the first pivot, I look for the next non-zero column. Well, this is where the shading comes out. Basically, you sort of ignore that and look for the next non-zero column, which in this case is the third column. That makes this the next pivot column, and then you pick a non-zero entry there, which you could do either one, but I think I picked, I don't know what I did. Well, it's debatable. I guess I picked the -3 one. But anyway, I did some row operations here, and that changes this to 1, -1, 1, and 0, 0, 1. At this point, we're at the REF, and then the backwards pass here is really silly. It's just clearing the 1 above the 1 here, which gives us 1, 0, 0, -1, 0, 0, 0, 1, 0. That's the REF. All right. Okay, so I guess I could show you. Oh, yeah, I guess this is not a bad example to mention because it's just so silly. Silly examples aren't bad to talk about. So if I just have a single row, what does the REF do? Well, it just rescales that 2 to a 1, and there you go. That's REF of V. Yay. And that's true for any real number R. I don't know why I felt the need to put a variable in here just to mess with you, I guess, but that it does bear that is something I should mention, which is we can do these row operations with variables in the mix. I don't have any of those examples for today, but there are a couple of those in your homework. Here's another easy example. So I have to put the 1 up to the top. because the pivot row has to be, it's top down. So I swap it I could have either swapped 1 and 2, or I could have swapped 1 and 3. Either choice would have been fine, but I swapped 1 and 2, put the 1 up there, and then I subtracted 3 times row 1 from row 3. That gets me to this, and we're done. So in this case, there is just a pivot column, and that's that. Now at this point, it doesn't really have anything to do with a system of equations, right? We've left systems of equations behind at this juncture. We're just doing this thing to a matrix, right? This row reduction to a matrix. We have, at this point in our thinking, we're not talking about a system of equations anymore. We're just talking about something you can do to a matrix, all right? And well, here's another lengthy example with, let me get back to my handwritten ones. Where was I? So example, all right, I'm going to foolishly attempt to sit down. I sure hope this is not a bad idea. Otherwise, all right, try not to. The problem is if I sit on the edge of the chair, it gets me. Eventually, you'll be old and know what I'm talking about. All right, here we go. Here goes. No, my camera's unplugged itself. All right, get back in there. No, you go to your home. Stupid power cord. Come on. You can do it. All right, there we go. I'm gonna get like a rubber band to keep the power cord from coming out. Man. Sorry guys, but I must do this. For I still have. Come on. What's going on here? Oh, I'm trying to put it in backwards. That's probably not wise. All right. Technical difficulty intermission brought to you by stupid power cord. All right, now, ooh, a mistake. Now, here's yet another example. So, just to try to recap here where we are, what we're doing, where we're going. This is our method to solve systems of equations, is row reduction. The ways that I was doing it in the first class, those are sort of weapons of last resort. Now, if your system is really, really simple, maybe you don't need row reduction, right? Maybe you can just kind of use the ad hoc techniques that we did the first class, right? But if the system is, more substantial, then you definitely want to use these matrix techniques to take it apart. So here's 4 equations and 4 unknowns. It is homogeneous, all right? Here's the coefficient matrix, 0, 1, 1, 1, and 1, minus 1, minus 1, 1, 0, 0, 1, minus 1, 2, 1, 0, minus 1. One of you I was talking to had put W as the first variable, so that's fine. There is a certain ambiguity here. Which one comes first, which one comes last? That's really just a matter of labeling. But I just put W as the 4th variable. That's just my default. But if you put W as the first variable, I'll figure it out probably, unless you. Well, anyway, if you're consistent, I'll probably be able to understand what you did. So my first move here is to get a pivot position up to the top row. See, I don't have it in my my non-zero leftmost row. I need that 0 doesn't do it for me, so I have to swap row 1 and row 2. So that gives me this, and then I clear out below that by subtracting 2 times row 1. It gives me this, and then okay. So what's the next pivot? Well, the next pivot would be from column 2 because that's non-zero. And it's non-zero having a non-zero entry, not just in the previous pivot row. That is why the paragraph in the thing I was projecting that I just showed you from my notes, it's like a page of writing because it takes a lot of words to pin down what we're doing. But once you get the hang of it, it's not that complicated. And once upon a time, we taught this to high school students. Not me, but people who are dead. So, oh, wait a minute. Seems kind of morbid. Maybe they're alive. I don't know, but I don't think it's taught in high schools much anymore. Maybe there exist northern high schools. I don't know. Let's see here. In other countries, there exist high schools. That's for sure. So, anyway, that's my next pivot position, and then I clear out below it, as you can see here. And then my next pivot position is that. It's already cleared out, and then great. Okay, so this brings me to my next notational device, which is the squiggle. You guys are going to like the squiggle. But I should warn you, the squiggle is dangerous. Why is it dangerous? Well, you see, I have a hard time giving partial credit if you use the squiggle notation. You know, if you tell me I did this, and you get something that's not what you should have, but then I can see, oh, you switched the meaning of 4 and 3 or something. Like, maybe there's hope that I can cipher what you did wrong and give you partial credit meaningfully. But if you use a lot of this, it gets to a point where I just can't tell if you're just completely wrong or if you're just a little bit wrong. And it's much easier for me as an instructor to judge a little bit wrong if there's details. Now, that said, this squiggle notation definitely has its place. I'm not saying you shouldn't use it. I'm just saying you should use it carefully. And so whenever I make this kind of partly condescending speech about how you should behave, I inevitably make a mistake. Hopefully that hasn't happened this time. So basically my point here is that once I get to this, I'm at the REF. All right, I'm done with my forward pass. And to make the backwards pass, I want to clear out above the pivot position. So all that's going to involve is just systematically, subtracting or adding copies of the fourth row to the third, the second, the first. And when I do that, because we got 0, 0, 0, 0 here, nothing happens except for that green column, which basically you just achieve an E4. Then you go to the next one, and I use the next pivot position, which is 1, to clear these guys out. That's what I mean by the squiggle, right? And then I clear out this pivot position above with this move here. Finally, I'm done because every non-zero row begins with a 1, and that 1 has zeros above and below it as appropriate. In other words, the pivot columns are the so-called standard basis, E1, E2, E3, E4. And something else went on here, right? If you know what you're doing, right, and you have a clear mind about what you're doing, you realize you could have omitted the 0 column, right? Now, if you do that, you should say something like, because the system is homogeneous, I can just row reduce the coefficient matrix, and from that I can cipher the solution. This only works because it's homogeneous, right? If the inhomogeneous terms are non-zero here, then all of these various row operations we did, well, they do something to those entries. But when these are zero here, and you do row operations, well, they don't go anywhere. They just do what they do, So that's one thing. So this had a unique solution, and the unique solution of this homogeneous system is, in fact, just the 0 solution. Yay! And there's something else, though, we should really pause and notice, which is that if we had a m by n matrix and we had an m by q matrix, right? In other words, the same number of rows, both have the same number of rows, all right? Then the first n columns of the row-reduced echelon form of A and the row-reduced echelon form of A with B glued onto it. So the way I read that, guys, is this is A concatenated with B. Of course, you could just say A glued to B if you like. But the point is that the row reduction, the Gauss-Jordan elimination, that's the name of that algorithm, okay? It happens, left to right, column by column, and so if I have extra columns, they do what they do, but that doesn't change what happens in the first n columns. All right, so the first n columns would be the same for both. And that actually means a lot. So let's see here, another example. So as the examples go on, I'm getting further and further away from a pure application of the Gauss-Jordan elimination algorithm, because you should understand that the algorithm is stated pedantically so that a proof can be given of its uniqueness. But once we get away from that, and we are already away from that because I am not going to prove anything in here like that for sure. That's for another class altogether. I'm just going to tell you it's unique, and we're going to operate off that basis, okay? And but once you know that it's unique, and you start to realize, oh, I can do more than one column operation at a time if I don't do ones which are self-referentially ambiguous. So let me show you some examples of that. Not the ambiguity, the doing it okay, I'm hoping. So I start with this matrix. And the first thing I did was I just, you know what, I don't like that 3, so I'm going to swap the 3 and the 1. I like to have a 1 in my pivot position, so yeah, I did that. And then I took that 1 and I subtracted it from here and here by doing row 2 minus row 1, row 3 minus 3, row 1. So that clears out this 1 and this 3. Bam. And then notice 0 doesn't do anything, so that stays 2 and that stays 4. On the other hand, this 3, the 3 did things because row 2 minus row 3, and this is the quintessential mistake, is to forget which step you're looking at and try to do arithmetic from the current step rather than doing it on the basis of the last step. That is the mistake. That is the most popular mistake, I think. If I had to take a poll. Anyway, so, row 2 minus row 1, so I go with the previous matrix here, and row 2 minus row 1, so 1 minus 1, 0, 2 minus 0, 2, minus 1 minus 3 is minus 4. That's why I got this minus 4 here. And then row 3 minus 3, row 1, so again, nothing happens because there's a 0 here, but this minus 3, row 1 makes minus 9, so 6 minus 9 gives me minus 3. All right. And then rather than waiting, and then I just went ahead and cleared out this one by adding minus 2 times row 2 to row 3, which gets me to this. And then what did I do? I divided this one, row 2 by 2, and I divided row 3 by 5 just to make all my pivot positions 1. And then the backwards pass here, I just did all at once. I added twice row 3 to row 2, and I subtracted 3 times row 3 from row 1, and there you have it. Yay. Now, I didn't even tell you what system this came from, right? There's 2 things we could do with this. Well, there's at least 2. There might be more. My imagination, my imagination just showed me 2 at the moment, okay? So we can take, one thing we can do is, if this is true, if we slap on another column of zeros, nothing changes. So the reduced echelon form of this homogeneous system is just that, which tells me that this homogeneous system, 3 equations, 3 unknowns, has just the trivial solution. I guess I should mention that. 0 solution. Also known as trivial solution. Which doesn't mean that it's trivial to find, but anyway. On the other hand, we could look at the given matrix M and look at it as a system of 3 equations and 2 unknowns. And if I did that, then I would have, I put the bar here, which is just decoration. It doesn't change the row reduction algorithm whatsoever, not even one little bit. And yeah, so we do the row operations, and same way, it would get us to this matrix with 1s down the diagonal and 0s everywhere else. And we go, oh no! Whenever that happens, whenever we have a non-zero row, which has a non-zero row which has a 1 in the rightmost column of the augmented coefficient matrix, that corresponds to the equation 0 times the variable plus 0 times the other variable equal to 1, which is not going to work for us, right? That's no solution. So this is an inconsistent system. So let me just take a step back here. So what you're telling me that this one row reduction tells me both the solution to a consistent system, consistent homogeneous system, and also a inconsistent non-homogeneous system? Yes, I'm telling you that. The same row reduction tells you about two different systems, all right? So this is one of the things, like you can't just think one-dimensionally about the problem of solving linear equations. That's a start, but there is more. There is more here. And I do try to expose you to that in the homework set, all right? The homework set does try to explore some of these nuances in terms of multiple interpretations of the reduced row echelon form. But first order of business, you need to get your row reductions down. You need to be able to do it quickly and efficiently, and just kind of have a sense of what you're doing. That said, if the question isn't actually to do a row reduction, if the question is just to solve the system, it's okay to do enough of the row reduction to make sense of the system, and then to kind of just bail, like in the middle of it. I'll try to do one of those like Friday, assuming we're actually going to meet in class Friday. I have hope. So I'll try to show you one of those kind of things where you use the row reduction to help you out when it's complicated. You get the system a little bit uncomplicated, and then you kind of like go back to the ad hoc methods of just solve and substitute. But sometimes I will ask you to do, use row reduction in order to to find the standard solution to the system. And when I say standard solution, that means you're writing the solution in terms of the non-pivotal variables as parameters. Let that be understood, okay? So here's a summary and some advice. When you have correctly calculated the reduced row, I can't say it sometimes, the RORF of M, the pivot columns will have the form E1, E2, Ek, where K equals the number of non-zero rows in the reduced row echelon form of M. Here is a general definition for the EIs. EI, the jth component of it, is Kronecker delta Ij. Fine, I'll spell it out. This is the Kronecker delta. It's one of my favorite things. The Kronecker delta, simple enough, it is 1 if I equals to j and it's 0 otherwise. And if you take the collection E1, E2, En, this is so-called standard basis for Rn, all right? So your pivot columns will be a subset of the standard basis of Rm if you have an m by n matrix. Now, if your augmented coefficient matrix, then the number of non-pivot columns corresponds to the number of free parameters in your solution set. In other words, let's see here, however, this is assuming it's consistent. I should say ... provided, that was supposed to be provided, I tried. This, not this. Provided this doesn't happen down here, right? If on the other hand your rightmost column in the augmented coefficient matrix is a pivot column, you're out of luck. That means that you've got an inconsistent system. You've got 0 equals to 1 as your simplified equation, which means there's no solutions, all right? And then number 4, and this is where the nuance is, all right? The theorem on page 4 that I shared with you means that we can focus on the leftmost columns of the reduced row echelon form of M and answer multiple related questions from a given reduction, like I just showed you. But there's another kind of application of this, a related application, I should say. If you had two systems and two different augmented coefficient matrices, however, both of the systems shared the same coefficient matrix, the same A, then if you were to do the reduced row echelon form of A with both of the inhomogeneous terms glued on, right, you'd actually be able to solve both of the systems with that one reduction. And I think I have at least one problem in the homework which explores that idea. And if I didn't get to it this mission, I'm sure I'll get to it in some future mission soon enough. Anyway, Friday, we're going to look at applications of linear equations, some things like curve fitting and maybe some traffic flow. We'll see what it gets to. But to start class, I'll just say, do you guys have any questions about row reduction? If there's something that's troubling you about it, we can just focus on that to start with before we get into any applications. I'm sorry I went 5 minutes over here, but I will send in the announcement that you can watch this at double speed, so you just got out like 15 minutes early, maybe 20? No, wait. Yeah, 25 minutes early in view of that. Anyway, I'll shut up. This is just getting stupider. Thanks, guys.